Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey, what's up everyone? I recently attended the AWS reInvent conference in Las Vegas, and I'm excited to share a few of my many interesting conversations from that event here on the podcast this week. Before we dive in, I'd like to thank our friends at Capital One for sponsoring our reInvent series. Capital One has been a huge friend and supporter of this podcast for some time now, and I'm looking forward to sharing my interview with Dave Castillo, Capital One's Managing VP of Machine Learning, with you on Thursday. Dave and I discussed the unique approach being taken at the company's Center for Machine Learning, as well as some of the interesting AI use cases being developed at the bank and the platform they're building to support their ML and AI efforts. To learn more about Capital One's machine learning and AI efforts and research, visit capitalone.com/tech/explore. And now, on to the show. All right, everyone, I am here at AWS reInvent in Las Vegas, and I am with Feng Yan. Feng is an assistant professor at the University of Nevada, Reno. Feng, welcome to the TWIML AI podcast.
Thank you.
So you just did a talk here on one of your research projects, which is focused on, or it's called ALERTWildfire, and it's focused on detecting wildfire smoke using machine learning. We're going to dive deep into that. But before we do, how did you get started working on this problem? What's your background and how did your interest align with this particular problem?
So my background actually, lies in machine learning and computer systems. So sort of, cross-discipline between these two areas. So actually, when I'm doing my PhD, I actually have like a more computer system background. So we can build, efficient, systems for data centers, for, cloud. And then, I had an internship in Microsoft Research, and that's where I actually started working on machine learning. So I still remember, like back then, we had a machine learning system. At that time, we didn't have TensorFlow, didn't have MXNet. We actually had a system called Atom. So that's actually, the state-of-the-art system back then.
Okay.
And, I'm extremely lucky to have the opportunity to work with the group to work on this system. So that's where I started actually working on the machine learning. And it's actually back in 2014. So it's actually, before, even the AI and the machine learning, becomes really hot and popular.
It's current wave.
right.
Yeah.
Before actually the wave, yeah. So, and then later I joined the University of Nevada, Reno, and become a faculty there. One a special thing, right? Because I used to be in the East Coast. After I moved to the West Coast, we do see, right? One specific situation here is about the wildfires, right? They actually, Nevada and California, they have a lot of wildfires, which significantly impact the air quality and the people's life. Because the smoke contains a lot of particles that's bad for your health, and also it will create this low visibility situation that's dangerous for a lot of things, and it also creates this dry condition, and which will lead to even more wildfires.
Okay.
So that's why I started to get kind of curious about, right, how whether there's any efforts has been made into kind of monitoring, control, the wildfire and also the wildfire smoke and air quality. So, and very likely, UNR has a team led by Dr. Graham Ken and Ken Smith. They lead the seismology lab there, and they actually had an effort to build a camera system to help to monitor the wildfire. However, current stage they are basically doing things manually. So from computer science perspective, I'm thinking, right, so with my background in machine learning and cloud computing, I'm wondering whether I can help them to build like a more intelligent system. So that's where we actually started to think about this project. And later we worked together and actually got NSF and AWS co-sponsored big data grant to work on this project. So that's how I actually get into this topic. And,
cool. So yeah, and that's very fortunate that you walked into this environment where they've already got these cameras deployed to try to solve this problem, but no automation system in place.
Right.
How many cameras have been put in place to monitor the wildfire situation?
Right now, we have like more than 150 cameras already deployed, and then there's hundreds more, is going to be deployed soon. This is the camera system that's specifically built for monitoring wildfire. Okay. And the technologies we developed to actually use machine learning, edge computing, cloud computing to help the monitoring accuracy can be extended to even the general camera system. We don't have to be constrained by like a specific network, because right now there's a lot of camera system, right? They used for traffic and other purpose. They are already being there, right? But the technology can be extended to other systems if needed.
Okay. And how are the cameras deployed? Are they in a grid like in forested areas, or are they in more populated areas but facing edges of forested areas? What's the rationale or methodology behind the camera system?
The camera systems, they basically based on the areas that are more like prone to fires, of course, right? And of course, the specific actually technology about the camera itself is actually led by the group of the system technology lab. So we are more kind of on the software side.
And so when I think about monitoring for wildfires and images, one of the immediate thoughts is like satellite imagery.
Oh yes, that's a very good question. Conventionally, people are using satellite imaging as well as meteorology to do the wildfire smoke forecasting and also the air quality prediction and forecasting.
Okay.
So the limitation of this conventional technique is their resolution. So actually, wildfire smoke, they can transfer actually very fast. Like we had like a video, this morning to show to the audience that, for example, for like a metro area of Reno, like the whole metro area has close to 1 million people. So it's not as big as Vegas, but it's still quite a big area. So actually, in a windy day, the smoke actually can spread over the entire city in just 20 to 30 minutes.
Oh, wow.
So, yeah. So for the conventional methodology, their data is very coarse-grained. For example, right, in terms of both time dimension and also the spatial dimension. For example, for the time dimension, actually, the data, right, no matter satellite image data or meteorology data, they refresh like every a few hours or even like at the day's level, right?
Right, because you've got to wait for a satellite to be overhead.
Right. So, and another thing is about the spatial dimension, right? They basically have like, for example, the typical resolution is like 10 by 10 kilometers. So this is like pretty big, right? In terms of, the forecasting. And think about it, right? If we do want to like accurate forecasting, for example, for an area of a city or like a neighborhood, right? So we do need a much finer grained way to track the smoke and also to the air quality prediction. So that's why, right, we are thinking about, using the camera data, right? Because camera data is very fine grained, right? Mm-hmm. You can, capture the image like a dozen of them per second, right? And you can basically have infinite resolution as long as you have enough cameras, right? We sort of use like a hybrid approach to combine both the conventional data, like satellite imaging and as well as the meteorology data together with this camera data so that, we can have like a much finer grained data. And another important thing about the traditional approach is, for example, for the satellite data, since it's shooting from the app, right? Actually, like a cloud and other situations can block the view, right? So that you will have a lot of missing data. And while camera is actually on the ground, so it basically have like a better view, right? But of course, problem with camera data is right. They only have local views. They didn't have like a very good global view. So that's why it's kind of complementary to each other, right? That's why we need both of them.
Your collaborators that deployed the camera system, did you say they're with the Department of Seismology? Like, are they originally trying to detect earthquakes with the cameras, or?
Actually not. Like they, I think they just had this idea, right? Because, in Reno, we have a lot of, wildfire and smoke like situation. But right now they sort of just deliver the camera data to for example, the firefighters, right? So that they can manually check whether this area has a fire, and if so, they can use it to monitor it. But it doesn't have any kind of intelligent way to automatically alert when there's a fire or smoke, and it doesn't actually track the fire or smoke right automatically.
So you've got this data coming off of these cameras, 150 today. Sounds like 10 frames a second, you were saying? Or 10 frames a minute. I remember 10.
Right. This is actually a parameter you can control, right?
Sure.
Yeah,
sure.
You can, make it like 1 frame per second or even 1 frame per minute, right?
Yeah.
But you can also up to like maybe 30 frames per second, right?
Yeah.
So that's why, you have a lot of data actually. It's significantly
That's what I was getting
more.
At, how much data that
right, exactly. Yeah. It's the scale is so much bigger than the conventional like satellite data or the meteorology data.
Mm-hmm.
So that's actually our focus, right? So think about in practice, right? Even though you have these cameras ready, right? You can have a lot of data coming from the sensors, and then you also have the models, right? For conventional statistical models as well as the new kind of machine learning, deep learning models, right? But between the data and the model, right, you actually need to collect and deliver the data to the model, right, in a timely way, right? Yeah, so that's why one of our efforts is how can we do some pre-processing at the edge side, and then to make the communication or transferring the data more efficiently to the cloud. So that's why we have this edge and the cloud working together to actually deliver the data in a timely way. And another important thing is when you have this massive amount of data, right, you do need to find an efficient way to process it, right? Because if your prediction detection is too slow, then basically if the fire or the smoke is already past that region, right? Then it doesn't matter, right? So you have to do this, fast enough to make it proactive.
Yeah.
Right. So that's why a lot of effort also being spent on how can we do like things in like low latency, give good scalability, and as well as more efficient, right? Because whenever you talk about this massive amount of data and very complicated machine learning algorithms, right? So they basically consume a lot of computing resources, right? A lot of energy, a lot of computing resource. That's actually at this scale, it does matter, right? So that's why we consider both the latency, scalability, and efficiency into consideration for designing our system.
Let's maybe dig into the model itself and the process you took to develop the model. Sounds like the inputs are these images. Are there other features that you're feeding into the model? And what is the model ultimately trying to do?
Yeah, so this is just between us. So actually, since this project starts from the beginning of this year, so we are still at quite early stage. So some of our efforts in the models and the training pathway is still ongoing. So that way it's not yet to show, because some of them are submitted for publication, some of them are still in the
okay.
So actually the talk this morning, of course, we showed some preliminary results about how can we use machine learning models to actually detect the smoke, and I can share a little bit about that.
Okay.
And then actually another thing we have already accomplished at this stage is after you have the model, right? You do need to do the inference or classification or detection, right? So this is also like a big thing, right? You need to do this in like a real time, right? Maybe I can talk a little bit more about this if you want.
Okay. So maybe let's start with the results that you presented this morning.
Okay.
Maybe a good place to start there is how are you formulating the problem that you're trying to solve? Is it a classification problem that you're trying to express it as, smoke or not smoke? Or are you trying to determine how much smoke there is? Are you trying to determine predict the future likelihood of smoke? How do you structure the problem?
Okay. So for the problem, first of all, right, for the processing the camera data is actually our focus of this project.
Okay.
So of course, we do have a lot of fancy machine learning models right now, right? However, these are more kind of towards like this benchmarking, right? So the data is more or less defined, right? So one big challenge of detecting smoke is think about it. The smoke is actually has like a various shape, right? I would say, right, in this world, maybe no two smoke looks the same.
Right. So in other words, like you've got all these, we've got, these models like ResNets and other things that are, trained on things like ImageNet, where you have these very well-defined objects in the scene. And I guess they also have kind of technical parameters like, they're 224, dimension images, and you've got this stuff coming off of a camera, so real images, of things that for, most of the time you see them in a picture aren't even really there.
Right. Exactly. So actually there are two challenges, right? One is about the environment, right? Think about in a real situation, you have different light conditions, right? And then you also have various background, right? For example, in like a mountain area, right? When there's cloud, right? Then basically the cloud and the smoke can look very identical, right?
Yeah.
Even, humans are difficult to tell the difference.
Right.
And also the smoke itself, right? First of all, it has various shape, and the second is actually changing, right? The shape is changing over time, right? So that's the two challenges when you want to classify this, right?
And so, what has been your approach for overcoming those challenges?
Yeah. So actually, we at this stage, right? We tried some standard kind of models, and we did transfer learning. And for some like easier like things, we actually can do already very well with existing techniques. But for some more kind of challenge, right, background or some like fast changing smoke, it's we are still trying to find a way to solve it. It's still like ongoing project.
Okay. It sounds like at this stage, the model formulation or the problem formulation would probably be something on the simpler side, like just a classifier, smoke or no smoke.
Yeah. So for smoke and no smoke, right, we actually have already done some preliminary like testing, and it's actually can work very well, except some like really challenging things.
Yeah.
And our eventual goal is so we can actually not only identify with smoke or no smoke, but also we can identify the density of the smoke, right?
Okay.
So and then use that to map to like air quality, measure, so that we can directly tell from the image about the air quality, basically.
Okay.
Yeah, and another big challenge when you want to do the machine learning in this classification task is you don't have the label data, right? So currently we are still trying to use some supervised ways to train the model and to do the classification. But eventually we do want to utilize semi-supervised learning and unsupervised learning so that we can use the camera data directly, right? Raw data to help building models and improve the models.
So you've got some preliminary models that you've developed that can start to differentiate between smoke and non-smoke, and you're continuing to work in this area so that you can do things like identify density patterns and things like that. But the main focus of the work that you've done thus far and have published on is, it sounds like, on the inference side and maybe some of the characteristics related to the edge nature of the camera deployment. Are you taking advantage of, actually is more of a question than a statement, are you doing like inference at the edge? Is that part of what you're trying to build towards?
Yes. So for the edge part, it's still ongoing. So what we have done so far is about how you can do efficient inference at the cloud side.
On the cloud side. Got it. Okay.
So on the cloud side, right, if you think about it, right, about a camera network system, right, when you do this tracking and prediction, basically there will be cameras join the network and leave the network, right, because the smoke may spread into like a new area, as well as the network condition is very unstable. Right. So basically you have this kind of dynamic workload, right? Because the number of cameras and number of requests sent to your to the cloud for classification and detection is actually changing over the time, right? And especially, for example, right, when the smoke moving to like a metro area, right, where we do need to pay like more attention, which means we may need a finer grained prediction, right, because the smoke can transport over to like a neighborhood, right, in like second level, right. So that's why usually when the smoke approaching to like a metro area, you will have suddenly like a very high number of requests you need to process, right?
Okay.
Because one thing is you have a lot of cameras, right, in metro area. The second is it's very important, right, to detect and to classify and detect things timely in a metro area, because there are denser populations of people, right? So in this case, when you have this kind of suddenly increased demand for inference, then you do need to have like a good way to scale, right, in the cloud. So we have a joint work with Hong Kong University of Science and Technology, where we did like auto scaling work. So right now, Amazon do have something called SageMaker that can automatically scale your number of instances to a high level when it observes increased load. However, this is very cost-grained approach. First of all, it's a feedback approach. So it observe and then act, which means it takes quite a while between it observed the high load and it actually scales. Usually this is at a few minutes level right now. However, right, if you want to do this real-time fine-grained monitoring of smoke, then basically you need to do things at the second level, right? So that's why we created like a new system called Mark that can have much quicker scalability than SageMaker. So the key idea here is, right, so SageMaker is sort of feedback way of doing things, right? It's observe and then interact, right? And there's another way you can do is over provisioning, right? So basically, I predict there might be like a higher load, right? And then I increase the resources in advance, right? And of course, right, in this way, you will have extra cost. And another thing is you cannot always predict, right, correctly. For example, right, if you look at the load curve, usually just like a stock market, right, it's randomly and can surge very high sometimes and then suddenly drops, right? So in this case, if you cannot predict the load like accurately, right, then what can you do, right? So our solution is combining the infrastructure as a service together with function as a service, or the popular service provided by cloud providers. Okay. And the idea here is, right, we still would like to use infrastructure as a service because it's much cheaper in terms of cost. However, for function service, it uses a container, right? And it can scale very fast at like a second level. So for the normal load, right, we just use the infrastructure as a service, those virtual machines, to provide the main computing power. But when there is a surge of load, right, of course, we will do some predictions, right? If the prediction is accurate, then we can do provisioning. But if it fails, we will use the serverless instance as a transition period, so that it can immediately take the new load while you are starting new virtual machines. And once the new virtual machines has been started, basically the serverless instance can transfer the work back to the infrastructure service, so that you will have like instant scalability while also control the cost.
Thinking about this in the context of cloud, this is maybe, I don't know if we talk about this a whole lot nowadays, but we used to talk about this concept of cloud bursting, where you'd have like some normalized infrastructure capacity within your enterprise, and then you have some burst of activity and you process that off in the cloud. This is like function bursting or something like that, where you're running everything on instances in the cloud and then bursting into Lambda for excess capacity.
Oh, yes.
That's the general idea?
Yeah, it's very similar to the concept. But instead of using purely, Lambda, for example, right, we actually did some experiment and find, right, if everything is on Lambda, since machine learning is very expensive, right? You actually need to much higher cost eventually. So that's why, right? So we had this idea to combine the infrastructure as a service together with the function as a service to enjoy the benefit of both worlds, right? One is cost efficiency, and the other is instant scalability. Yeah, another thing, we didn't use the function as a service at this stage is they do have some limitations about, the model size, like the function size you can actually have.
You only get a certain amount of memory and a certain amount of execution time, that kind of thing.
Yeah. And we actually have some effort is pushing on, enabling the function as a service to support these larger models. Yeah, but it's still, undergoing, so I cannot share too much details at this stage.
So what's interesting about this to me is that independent of the domain that you're applying this to, as more folks are moving machine learning workloads to the cloud, it gets more and more important to figure out creative ways to cost optimize, like building systems to move stuff over to spot instances versus regular instances. And this is another kind of way to arbitrage the cost difference between one service, the functions versus the infrastructure.
Yes. So actually, the cost plays a very important role here, right? Because think about this is a service, this is a continuous, process, right? It's not just one-time effort, right? So that's why, right? If you think about the accumulated, the cost and the benefits, it's quite significant, especially for this machine learning, right? models, they are quite kind of intensive, right? They consume a lot of resources.
And so have you been successfully doing inference on Lambda, or are you using some other functions capability?
Yes, we did actually being able to deploy some relatively smaller models on Lambda. However, for some larger models, right now we are still, have some ongoing efforts to make it being deployed on Lambda.
There are two aspects of what you're doing. One is focused on how to achieve the scalability requirements, and this is this idea of bursting the Lambda or the functions. You also mentioned an element of this that's focused on latency. And what's the driver there? Is it just decreasing the amount of time it takes to get a prediction out to someone who can act on it, or is there another consideration?
Oh, yes, this is a very good question. So about the latency part, actually, it's very critical because all these, machine learning models, they do take a lot of time to process a request, right? Think about, for example, right, the inception model, right? They have hundreds or even thousands of operations, right? So basically, each image you send, they need to go through all these operators, right? So if you're doing the sequential way, of course, it would take like a lot of time, right? Can be like seconds to even minutes, right? So one way to accelerate the processing speed is through parallelism, and also batching. So for the parallelism part, so basically almost all modern machine learning inference or serving frameworks, they do provide these control knobs. Usually you can have the request level parallelism as well as operator level parallelism. For example, at the request level, basically means you can process multiple requests in parallel. Right, this is like just like traditional serving. It's very easy to understand. For the operation level, basically it means how many threads or how many calls will be assigned to execute each operator. So since operators, they do have dependency, right? So it's quite complicated, how you configure, this parallelism, right? Some people may say, I just set it to maximum, right? If my CPU have 20 cores, why I just set 20, right? However, this the experiments shows it actually doesn't work ideal like this, because the more threads you will have more contention for the resource, because we know we have limited cache bandwidth, also the cache capacity, right? So if you have too many threads working on just one operation, sometimes it will cause contentions, and actually this will create even more overhead and slow down your processing. So that's why, it's not always like you set things as maximum would give you the benefit. We actually, find most of the time, actually, it's just a random value in between, depending on your model, depending on the specific system. Yeah, and another important aspect is batching. So the batching basically means...
Before we move on to batching, when we're talking about operator parallelism, what's the operator in this context?
Oh, yes, that's a good question. So for the operators, right, basically you can think about, right, no matter, what models you have.
Are we talking about things like low-level things like multiplies and accumulates and that kind of thing? Or
yeah, so modern machine learning frameworks, they actually take your model as input, and then they will create a computational graph, right? For example, some operators, doing like matrix multiplication, right? Some just like a symbol, like element-wise operation, right? So all these operations basically are executed in your system.
So we're talking about kind of unrolling the computational graph and understanding how it can be parallelized across multiple cores.
Right, exactly. So, however, the thing is, all these frameworks, they provide, a control knob so that you can set, different parallelisms for operators as well as for request. For request, basically, it's admission policy, right? However, the thing is, they didn't tell you how to set it for a specific model and deploy it in a specific system.
Okay.
And we find that if you set it in a different way, it actually can significantly impact your latency.
All right. And so you're about to mention the second part of latency, which is the batch size.
Yeah. So another important thing people do for accelerating the processing speed is batching. So basically, batching means you just you don't execute a request one by one, but rather you will form you will put several images together into a batch. So the benefit of batching is, right, it creates more opportunities for optimization, right, parallelism optimization, right. For example, right, if you have like a small matrix, right, because it when you do, for example, matrix multiplication, right, if you have two small matrices, of course, things can be done in parallel, but in very limited degree. However, if you have two big matrix, right, then basically you can divide them and beta accelerate them, right. So that's why the batching can actually helps the efficiency of the computation, right. So all these low level libraries, they actually developed to optimize the computation when you have like a larger degree of input dimension.
Okay.
So, however, right, batching have two sides, right? One is it can increase the computational efficiency and then accelerate, the overall computation. Mm-hmm. However, if you think about it, in order to form like a large batch, right?
You're increasing latency.
Right. It's not in a training, right? Because in training, all your data is there, right? You can create whatever batch size you want.
Right.
But in the real-time inference, actually request arrives in a random pattern, right? Mm-hmm. Sometimes, there are more requests, sometimes less requests, right? And if you want to create a larger batch, means the earlier arrived request, they actually have to wait the later request, mm-hmm. right? Then this penalizes the earlier request. Another thing is, right, even though when you, for example, put 10 requests together, right, it's faster than, execute individual of them. However, it still takes longer, right?
Right.
Say each request takes 100 milliseconds to process, right? Then if you do one by one, then you need 1 second, right? However, if you do it in a batch, maybe it's just 500 milliseconds,
sure.
right? Then still think about the first request. Originally, it only takes 100 milliseconds, but now it takes 500 milliseconds, right? Of course, the later request will benefit a lot from this because think about the queuing waiting perspective, right? Mm-hmm. They need to wait the earlier request finish, right? Mm-hmm. They can immediately go through the process and it's doing faster, right?
Yeah.
So that's the reason you cannot do an arbitrary batch size, right? Mm-hmm. So actually, modern machine learning frameworks, they do provide two control knobs here. One is the batch size, maximum batch size, which means once you hit the threshold, it will be sent to the system, right? Even you have even more, it still just send this size. The second is something called waiting timeout, which means you don't want to wait forever to create a batch, right? Since we are talking about latency, right? Every request matters, mm-hmm. right? So, however, set these two parameters in a real system is really complicated, right? It mm-hmm. depends on a lot of factors. So, if you think both parallelism and batching parameters, right? We have actually a lot of parameters here you need to tune, right? Mm-hmm. I would say even system expert and machine learning expert, right? They work together. It's difficult, to find a way to just manually tune these parameters. Mm-hmm. Plus, based on different system situation and different workload, right? These parameters need to be changed, right? So that you can achieve the optimal, right? So that's why, we created an automatic way, to help people to configure these parameters. So our actually first work published in Supercomputing in 2016, we actually built a queuing model to actually, to model the situation, when you have, these different parallelism.
Okay.
And then we can mathematically, compute optimal solution for the scheduling.
And this is all bringing me back to the stuff that I did in grad school.
Oh, really? Wow.
Queuing theory and
queuing
stochastic
theory
modeling
and
MMN queues and all that kind of stuff.
Yeah, you name it, right? Yeah.
Nice.
And of course, the limitation of that work is, right, you do need to have some assumptions, right?
Right.
For example,
IID, arrival.
Yeah. You do need to assume the random arrival, right?
Right.
Which follows the ID distribution,
right?
And also, for that work, we also assume, the request size are deterministic, which means it's actually true for a lot of computer vision tasks, right? Think about all the pictures, they have the same dimension, right? And the model is the same. Of course, they take roughly the same time to process, right? However, this is not true actually for some other applications like, speech recognition, right, for natural language processing, right? So it depends on your sentence is short or longer, right? The processing time can be different. Think about, right? So basically the model-based approach, they do need some assumptions, right? So, and if we want to make it more general in practice, we actually, there's another ways doing model-free approach, right? Of course, there's tons of different learning-based approach for model-free, right? So, of course, right, some simple things like a Bayesian optimization, right, is also very popular, right? So the reason we choose reinforcement learning is because think about the dimension here, right? We actually have a lot of parameters you need to tune, right? So it's actually, multi-dimensional problem. So quite complicated. So that's why we choose the reinforcement learning as our approach, right? However, for reinforcement learning, there's a big limitation. It needs a lot of training samples and it converges very slowly, right? So this is actually not ideal, right? In a real-time system, right?
Right.
So also it creates a lot of overheads.
Those problems are training time problems as opposed to inference time problems. Yes or no?
If you want to use a reinforcement learning to configure your system, right? Then this is like a training problem. But of course, it's different than. So we have two machine learning parts, right? One is machine learning itself, right?
Yeah.
And the other is to configure the system parameters. Right. So we actually use a machine learning model to find, optimal solution to do the machine learning inference.
Right.
It's
right. Yeah.
So the conventional reinforcement learning, right? They do have a relatively long learning cycle. So what we observed is for this specific problem, right? So think about it, right? When you have this complex computational graph, right? You may have hundreds of different operators, right? So some operators may be more sensitive to this parameter, right? Others may be more sensitive to other system parameters, right? So when you do a very slight change, right? For example, just one of the parameter increased maybe from 2 to 3, right? So in this case, actually a lot of maybe only some of the parameters they have pronounced change, but most of others maybe not so much, right? But global situation is that it doesn't show much of the change, right? However, if you did a big change, right, then almost all of them have different behaviors. Then this will show more kind of pronounced changes globally, right? So if you draw a heat map, right, you will see, right, when you have a big change, the latency will be totally different. However, if you zoom in, right, say I just do a small change, actually it's locally it's very smooth. It actually doesn't change latency much, right? So then we are thinking about, right, why we just do less of the the learning samples, and then we use the one learning sample to actually help estimate, right, the nearby regions. So that's why we created an approach called region-based reinforcement learning, or RL in short.
Okay.
Yeah. So we find compared to state-of-the-art reinforcement learning approach used for system configuration, we can significantly reduce the learning curve. So basically, the reinforcement learning models can converge so much faster, and it also think about, right, it's a continuous learning process, right? So whenever you have your models changed, or even the system can have changes, right? Especially if it's a cloud system, right? Itself have a lot of randomness, right? So whenever there's a change, right, basically the models will learns to adapt to it, right? So that's why the fast convergence is critical here.
I feel like I'm close to understanding what you're doing with the region-based RL. What I am envisioning is you're doing something where you're changing your optimization, your cost function, so that you're more focused on kind of this coarse grain sensitivity analysis kind of thing.
If you think about reinforcement learning, right, it basically have two key things, right? One is action, one is state, right?
Right.
So it's just like we are running things or playing a game, right?
Yeah.
We would try different actions, right? And then we will get different rewards, right? Of course, in different state, you try different actions, you will get different rewards, right? So that's basically the space of the whole learning process, right? So our approach basically says, right, if you try one action in a certain state, right, basically you probably then need to try another very close by action, because it gives you will be roughly similar amount of reward.
So in other words, you're kind of quantizing the action space a little bit differently, more coarse grained.
Yeah, you can imagine that.
Kind of think about it,
right,
sort of like that.
Yes. So and of course, we do introduce like a hyperparameter, right, to see how big is the region, right?
Yeah.
So if you have like too large region, then it will sort of so the region size basically means, right, if you have like a larger region size, you will learn faster, but if it's too big, then you will never converge, right?
It's kind of like a learning rate.
Right. If you have like a too small one, of course, it will have less risk, but takes longer, right? If you have a size of 1, basically it's the traditional conventional reinforcement learning.
Right.
I think the key message here, right, is even if you have a good training model, right? So in order to do this, real-time detection is actually not that easy. So you do need to consider, the machine learning actually are quite expensive compared to conventional statistical models. And as well as, right, you do have this changing demanding of the workload, right? So that's why, right, you need to consider, the latency as well as the scalability. And of course, right, if you want to go to cloud, right, the efficiency is always a problem, right? If you have infinite amount of budget, right, of course you just go for the most expensive equipment, right? But it's not true, right? Actually, it's quite costly, right? So especially for machine learning inference, right? If you want to continuously rent, a lot of machines, right? The actual computing resource and energy is tremendous, right? So any savings along this line would be, give you like a huge benefit.
Awesome. Well, Feng, thanks so much for taking the time to share with us what you're up to.
Okay, thank you.
Thank you.
All right, everyone, that's our show for today. To follow along with our reInvent series, visit twimlai.com/reinvent2019. Thanks once again to Capital One for their sponsorship of this series. Be sure to check out CapitalOne.com/tech/explore to learn more about their ML and AI research. Thanks so much for listening, and catch you next time.